Between real and Fourier space that was not clear to everyone. And I had intended to cover this stuff before doing the BAO stuff. First, just a little bit of stuff to set up Gaussian random fields that we'll be using a lot in the next 2 days. And then a little bit about practicalities and how we actually estimate things in data. Yeah, so there will be more statistics and less physics in this one. Okay, so statistics, and there's a pretty nice review of perturbation theory and the statistics of random fields in this review article from 2002. Okay? But first we'll look at some background. So just a few quick things, right, to make sure everyone is on the same page. So we'll be talking a lot about probability distributions. We can talk about the probability x has some value. We make a histogram, right? So that's the probability distribution. We can take the cumulative, so an integral from 0 to x or from minus infinity to x. We can take the mth moment of the distribution. Yeah. We can take the Fourier transform of the distribution. Okay. The Fourier transform is sometimes called the characteristic function. In the language of distributions, we think of the characteristic function as a convenient way of packaging all the moments together. Yeah, because if I take the mth derivative of the characteristic function, when I take a derivative of the exponential, then I pull down an it. Sorry, I'm doing a derivative with respect to t, so I pull down an ix. And so each time you pull down an x, you're taking an average of dx, px, x, so you're getting the mth moment, right? And so that's the sense in which the Fourier transform packages all the information of the PDF. But it's a useful thing. But it will turn out that in a lot of the stuff we do in cosmology, there's a lot more physical meaning associated with this Fourier transform that we'll take quite a lot of advantage of. Okay. Okay. Let's. Next idea is if we have the sum of two random variables, then the distribution of the sum is given by integrating over all possible values of x, all possible values of y, and selecting the subset for which x plus y equals s. Okay. Strictly speaking, I should have written this in 2 steps. I should have written this as dx, dy, p of x comma y with the Dirac. Yeah? And so that has made the approximation that x and y are independent. In general, that won't be true. And when we want to use this in Gaussian random fields, then we will have to be slightly more careful than how it's written here. But the logic that you always integrate over all the variables with a Dirac delta to impose your constraint, that is general. Yeah. Sorry? Because I want to know what is the probability that the sum of 2 random numbers equals s. And so I take all the possible values of x, all the possible values of y, and I just take the subset where they sum to s. Right? So the Dirac delta is very convenient for this kind of thing.
So I missed how we could separate this into px and q.
Okay, so in general you cannot. So this is the general statement. If x and y are independent, then I can simply write this as the product of the 2 distributions. But if they are not, I cannot. So this is the way it's usually written. If I was doing something like, so I use s for the sum, but often in an experiment, the signal you measure is the true thing plus noise. Okay, so then you would say, if I make many measurements, then those measurements are always the correct answer with some noise on them. And that means that the thing that you are measuring is a convolution of the true thing with the error distribution. And usually we assume that the error distribution is independent of the true thing. And so this is usually the way we write it for error distributions. Therefore, the relationship between what you measure and what is the intrinsic thing. Okay. The important point is that whether I decided to write this as joint or not, you'll end up having something that looks like a convolution. Okay. And anytime you have something that looks like a convolution, then if you took the Fourier transform of this guy, so then you will have e to the its. When you take the e to the its, then you can split the its into itx and its minus x. And so then you will get the product of the individual Fourier transforms. And so that's a useful thing to remember, that in Fourier space, the product of the characteristic functions is the characteristic function of the convolution. And that's useful because oftentimes convolutions are painful things to do, whereas multiplication is easy. Okay? And so especially on the final day when we do the halo model stuff, we will be doing lots of convolutions, and we will always think in real space for the convolution, evaluate in K space by taking the Fourier transform, and then go back. Okay? And so this is a trick that we'll use a lot. Okay. All right. We'll be using a Gaussian PDF a lot. So a Gaussian is this functional form. The distribution of x has some mean value and some RMS value, some mean square value. Okay? And these are the only two parameters that matter. Okay? And if we take the Fourier transform of this guy, so the characteristic function of this guy, then it separates nicely into the piece with the mean and the piece that looks like the Gaussian for the variance. Right? So people made the comment the other day that, oh, the Fourier transform for Gaussian is a Gaussian, and that's the Gaussian piece. So it's if the mean was 0, then it would explicitly be this guy. Okay? I've written this also because some of the times we will need this non-zero mean in what we do probably tomorrow. Okay. Okay. So there's a useful way of thinking of this, which is, if I was doing n convolutions, then if I do n convolutions, then because these are both exponentials, the n just comes here and the n comes here. Okay? And so this is a useful thing to remember, that the convolutions are just changing the width of the Gaussian, right? And you're used to thinking of, if you make a measurement n times, then the error is decreasing as the square root of n, and this is that, right? This is the sigma maps to, so sigma squared maps to n times sigma squared, and so this is the root n. But you see it very simply with the characteristic function. Okay, okay. So we should remember this. If I have two Gaussians, and the two Gaussians have different variances, then instead of putting n, you just put the sum of the variances. No? Because you will still multiply the two characteristic functions. They have different variances, so what comes here is the sum of the variances. And so in data, if this thing had some Gaussian distribution and the error distribution was Gaussian with some different width, then the thing you measure will be a broader Gaussian because it was convolved with this guy. Okay? We're going to use this later today. Right? What's that? Yes. So suppose the distribution of t is a Gaussian with some width. And the distribution, so you're measuring it, but you make an error each time. Yeah. So that, let's say that the distribution of the noise is something like this. So then the thing that you observe, P of S, will be a Gaussian, but the Gaussian will be broader, P of S, and the variance of S will be the variance of T plus the variance of N. Okay, and so that's why the Gaussian is broader, right? So I was just saying, here was the special case where we were convolving things with N all with the same variance, and so you just see N times sigma squared. But if they have different variances, you just do the sum of the variances. So if I was now convolving, many different terms, then I would just sum up all the variances. Okay? All right. So there's a special thing about a Gaussian, which is when you do these convolutions, so when you take the product, because the characteristic function was an exponential, the convolution is also an exponential and has the same functional form, t squared with t squared. Okay? And so the convolution of Gaussians is a Gaussian. But in general, the convolution of two different distributions does not give you either one of those distributions. Okay? And so you will often hear in cosmology that inflation gave us statistics that are Gaussian statistics and that is scale-free. And the scale-free that people mean is the power spectrum of the Gaussian is a power law. Okay? That's what they mean by scale-free, but there's a much more powerful scale-freeness, which is that if you convolve a Gaussian with a Gaussian, you still have a Gaussian. And so why do I call this a more powerful thing? So let's think about the following. We want to say, or we often say the universe is homogeneous. Okay? So what do we mean by that? And in fact, yesterday someone even asked, no, on what scale is the universe homogeneous? Is it 100 megaparsecs, 50 megaparsecs? Okay? And so suppose I want to imagine that I'm describing the universe with a value of the density at each point in space. Okay? And supposing, it's not true, but supposing that the distribution, if I asked what was the distribution at any one point in space, so let's write a little bit more. Supposing I want P of delta at position 1, delta at position 2, delta at position n. I want this joint distribution. Okay? Then if I do d delta 2, d delta n, and I integrate over all these values, then I will be left with P of just delta 1. Okay? And this I will say, that's the probability that, any one point, a randomly chosen point, it has the value delta. Okay? And so we're imagining that this thing is a Gaussian. And we will define soon a multivariate Gaussian. Okay? But supposing that I want to now describe not the distribution of delta at this point, but if I was to take when I say this point, I mean at a randomly chosen point. Okay? But instead, I want to know what's the distribution of delta if I was to smooth with 50 megaparsecs. Because that's the kind of question we're asking when we say, is the universe homogeneous? We want to do some kind of smoothing. The operation of smoothing means, in the simplest, the way we usually think, we say, oh, I'm going to take everything inside 50 megaparsecs, and I'll take the average value. Okay? And so that operation means that if I imagine that at each point in space there was a value of delta, a different value of delta, then I want to do delta 1 plus 2 plus 3 plus 4, and all of them inside my 50 megaparsec box, and I want to take that average. So that means I'm doing the sum of delta 1 plus 2 plus 3 plus 4. So I'm doing the sum of many deltas. And I want to know what is the distribution of that sum. Okay? And so if the different deltas were all independent of one another, then I would have a convolution of all the deltas inside my box. And so I would have a very long sum. I would write it as this with many of these integrals with finally a Dirac delta. that the sum of all the 50,000 whatever variables, I add them all up and I get delta on 50 megaparsec scale. Yeah? So the operation of smoothing is an operation of summing random variables, and so is an operation of convolution. Yeah? And so that means that the really deep scale freeness of Gaussian fields is the statement that if my unsmoothed field, my unsmoothed statistics are Gaussian, even when I smooth, I will still be Gaussian. And that is a huge simplification. Imagine if the PDF on 1 megaparsec scale has a different functional form from 3 megaparsecs, from 50, from 100. This would be a real pain to work with. Okay, so we're very fortunate that the CMB sky looks so Gaussian that we believe it's a good approximation to use Gaussian statistics. Otherwise, courses like this would spend a lot of time on just what happens to the PDF. Okay, and so here we get to write down one PDF, and that's it. And that will be true for any scale.
To summarize, scale invariant in this case means that if you smooth the distribution, you'll still get a Gaussian.
You'll still get a Gaussian. The only thing that will be different is the variance will be different.
That's equivalent to a power law power spectrum?
Okay, so we're going to come to power spectrum in a second. It's not equivalent. So the way in which it is used is usually scale-free means power spectrum is the power law. Okay, and I'm trying to say that's actually a deeper thing. Okay, so now we will get into a discussion of the power spectrum, but we're not there yet. Right now we're fortunate that any scale is Gaussian. Yeah, okay.
I don't actually understand why it is smoothing as a convolution. You add up a lot of variables, independent variables, and say that it should be equal to constant. I mean, convolution means integral of probability, multiplication of probability of independent all of these points, and then derive delta over some equal to some constant. So what does this constant mean?
Okay. So let's come back to the example with two variables. Okay, and so here we had, we integrated over all the values of x and y. We put the Dirac delta, and we asked that they sum equal s. Okay, so if we do this, all right, then what will we get? We will get that this thing, the probability of s, is a Gaussian. So one way to say it is, if I want to know what is of all the ways of combining x and y, a few of them will give me s. I want to know what is the probability of getting this value. So this is what this represents, the probability of getting that value and no other value, s. Yeah? And so now I can imagine, for all my different combinations of x and y, sometimes s equals 1, sometimes it equals 2, sometimes it equals 3. I can make a histogram of how often a value of s arrives. So this is describing that histogram. So that histogram will have a Gaussian shape if the probability of x and the probability of y is a Gaussian shape. Just the width of that Gaussian will be different than of the individual x and y's. Yeah? And so it's saying if x and y have some distribution, then the probability of their sum also has some distribution. Yeah, because sometimes x can be, I don't know, -1, y can be +1, sum them to be 0, there's some probability of that. So, yeah. So the sums can give me any different value. If I want to know what's the probability that I got the value s, then I have to do this. Does that make sense? Yeah? Summing is the average. No, because I can divide by n, divide by 2. And if I'm summing 50, I can divide by 50. Yeah?
Sir, Gaussian we will get, if we start adding on, by automatically we will land to Gaussian. It is a thing.
Okay, that's the central limit theorem. Yes, that's right. So here we're assuming that we don't need the central limit to reach there. We're assuming that we started out with Gaussian distributions in the first place for cosmology. Yeah? It is true that when you add many things together, then you can go through, statistics proof of why the characteristic function will converge to this Gaussian shape. But we won't need that for this. Yeah? Okay. All right, so the operation of smoothing, of averaging, is like a convolution. Okay? And so the question of what is the scale of homogeneity, to answer that, we had to be able to do this operation of smoothing. Okay? And because we need to do smoothing, it means you should have in the back of your head, smoothing is convolution. Convolution means I should do in Fourier space. Okay? And so we will come back to this question soon. Okay? Thinking about how to do it in Fourier space. But let me just write out the Gaussian field, okay? And so the generalization from the simple Gaussian, the one-point Gaussian distribution, to one at many different values. So there's a bit of potential notation problem here. So let me state it. The reason I put x here is because we were using x and y, no, in the previous example. And so now I want to say, so now x is a vector for x1, x2, x3, x4, x5. And then I'll define this in a little bit. The potential for confusion is I was just now describing a spatial field where delta at position 1, at position 2, at position 3. And we often think of those positions as x. Okay? And so when I want to describe different spatial positions, I will do them like this. I will use delta at position 1, at 2, 3, okay? And it might be that you can think of it as delta at x1, delta at x2, delta at x3, and the short version for that is delta 1, delta 2, delta 3. Okay? And this matters because soon when we take Fourier transforms, we want to do Fourier transforms with respect to x, not delta, okay? And so just be careful. And if you're confused when the next slides come up about when we're taking the Fourier transforms, stop me. Okay? So the multivariate Gaussian is x is now a vector. The Gaussian used to be e minus x squared over sigma squared. So here's the two x's. And the thing that was the sigma squared has become a covariance matrix. And the covariance matrix has elements. Those elements are, you take all the values of x at, so if I want the element I and j, then I do xi, xj, and I do this sum. Okay? And so this one means the p of xi, the p of xj. So this one means xi, xj means dxi, dxj, xi, xj, pxi, xj. Yeah? Okay? We will almost always subtract, we will almost always subtract the mean values off, right? So the thing that is sitting here is always with the mean subtracted.
This is almost like the autocorrelation function.
Very good. So this guy will be the autocorrelation function. But this is why it was important that if I think of these as being delta at position I and delta, the fluctuation at position j, then it will be the autocorrelation function. So that's why I wanted, it's a bit confusing. It's not the position I and position j that makes the correlation function. It's the delta at position I and the delta at position j.
The random variable.
X is the random variable, which will be delta. That's right, okay? Okay, so did what he said make sense? Yeah, so if I have deltas at two different positions separated by some r ij, then this guy is the pairwise correlation function. Okay, good. So we can take, so if we think of this guy, then this guy is a matrix, and this matrix has elements everywhere. Okay? There will be a special one. It's possible that that matrix is diagonal. And that means, if it's diagonal, that means that the values at one and another are independent. If I was thinking of it as delta, then it means the delta at one position is independent of delta at another position. Okay? And so we have a special word for that. We call that white noise. But in general, a Gaussian field is not necessarily a white noise field. In general, the different values of delta at different positions can be correlated. And so in general, this guy is not diagonal. But you can ask, because it's a matrix, I can rotate and I can diagonalize it. And if you do that, then the x's, so the delta 1, delta 2, delta 3, those guys, right, they will, I will rotate, so there will be now some other transformation of those guys, some linear combination of those guys. So what is that? Okay. So that, the basis in which this thing is diagonal is the Fourier basis. Okay. And so here we go. This is, take the Fourier transform of this multivariate Gaussian. Okay. So then this guy will have the thing that was the mean mu before is now the vector of mean values, and the e to the t squared sigma squared becomes this guy. Okay. And so if you work this out, then you can find the basis in which this guy is just a diagonal guy, and that's the Fourier transform. Okay, so that's an exercise you guys should just do. Okay? And so that's very useful. Okay, because it means that if I want to describe the field, then the most efficient way of describing it is in the basis where this thing is diagonal. And the basis in which this thing is diagonal is the Fourier basis. And so we will exploit this in many ways now. Okay. Okay. Yeah.
You have written that for Gaussian field, C is diagonal. I mean, what do you mean C is diagonalizable?
So here C is diagonalizable.
Yeah. It doesn't matter whether it's diagonal or not.
No, it doesn't matter if it's diagonal or not. But if you were in the Fourier basis, then C is diagonal. Okay? Because the different, so if we were writing not delta at position x and delta at position xi and delta at position xj, but delta of ki and delta of kj, then that thing is 0 except when ki equals kj. Okay? And so the Fourier basis, this guy is a trivial thing. That means in real space, a Gaussian field is quite complicated because every position is correlated with every other position. But every k mode is independent of every other k mode. Okay.
So if it is slightly non-Gaussian, then that will reflect in the off-diagonal.
Okay. So if it is non-Gaussian, it. Okay, so her question was, will the non-Gaussianity reflect in the off-diagonal terms? Okay, so it is true that the off-diagonal terms in the k-space representation, that's where it's diagonal. Okay, so you can get coupling of k modes, okay, and that is one signature of the non-Gaussianity. But there are additional things that usually happen with a non-Gaussian field. And with the non-Gaussian field, basically this kind of functional form or this kind of functional form is no longer correct. Okay? So there's an important simplification, another important simplification that has happened with the Gaussian field. That simplification is that there were no things that depended on xi, xj, xk. Okay? And so, in principle, this could have been much more complicated. No, if I want to know about position 1 and position 2, maybe I need to know about position 3. And in a Gaussian field, I don't. Okay? Whereas in a generic field that is non-Gaussian, it's not just pairwise. Triplets can matter, quadruplets can matter. And so the general thing can be much more painful to work with. So the Gaussian is simple also because everything can be expressed just in terms of pairwise statistics. Okay. Okay. So yes, it can be infinite. So it can be.
You want to predict the field configuration over the whole universe. So that will have infinite variables. So in general, it is infinite diagonal.
That's right. So it's, right. So we think formally we think like this, but in principle we can think if I can partition space into arbitrarily small cells, and I will have many of these, and so it can be infinite dimensional. That's fine. Yeah.
Does the momentum basis becomes an ideal basis for this data?
It's just the characteristic of this functional form, right, of the Gaussian field. So if you want, you can go back. It's almost like the central limit theorem, okay? So it's really that if you start, the usual argument is done the other way around, okay? So usually you say, what happens if I made my k basis diagonal? Then what will the real space PDF look like? And you get a Gaussian. And if you have the diagonal basis for the k modes, do all the entries have equal value? Or do the entries have values that depend on k? Okay? So the values, that is what we call the power spectrum. Okay? So when this stands for delta of k1 and delta of k2, they are not correlated, but delta of k1 with delta of k, they're really Fourier transform, so it's complex numbers, so I have to do this one with the complex pair. Okay? But this guy is the definition of the power spectrum. Okay, so I have a slide coming up that will show that. And so that means that in the Fourier basis, this guy is a diagonal, and the elements down the diagonal are the power spectrum. Okay.
So one question. Right now we are doing the averaging over different field configuration.
Right, yes, that's right. You do an average over all possible waves.
Okay, so how is it related to the average over spatial at one?
So it goes like this, right? So this is the usual question is called the Ergodic Theorem, right? How do you relate the spatial statistics to this kind of discussion? Okay, and so the idea is the following. So we have made the statement that a Gaussian field means that I can make a Gaussian field like this. Let's make a simple Gaussian field. We will choose a random number. This random number is telling me the amplitude of a wave. I'll choose a random number. This one is telling me the phase of the wave. Okay? I have chosen the wavelength. So now I have a wave. Now I can take a wavelength that is different. I'll choose a random number for its amplitude, for its phase. I can add, so now this is a wave like this. Now I add my two waves, and 3, and 4, and 5. Okay? So I can build up my density field by adding up my different waves. Okay? This is one realization of the field. Okay? Now, I can repeat the process. Okay? When I repeat the process, then I will get another realization of the field, because when I pull the random number to tell me the amplitude of the wave, it could have come out with a different value. Okay? So now I make a different realization of the field. So let me do this 1,000 times. Okay, so now I have 1,000 realizations of a field. Let me go to the origin. So at the origin, I can ask what was the density at the origin? Of the origin of this guy, of this guy, of this guy. I'll have 1,000 values. So now I can make a histogram of those 1,000 values. That histogram will be the thing that we have just discussed, right? Because you average over many realizations of the modes. Okay? But I could do the opposite. I could do something else. I could say, okay, I calculate what is the density at the origin, but what is the density at some point in this realization that is not at the origin, but somewhere else? Okay? And I can do that. So in the first realization, a different position. Okay? And now for this different position, I can go everywhere else in space. Right? I can go to that far from the origin and get that density. And I can ask, what does that look like? Will also be a Gaussian. That Gaussian will also have will be the same histogram as the one at the origin. Because the K modes, they were chosen completely at random, so there's isotropy, homogeneity, no position is special. Yeah, so the shape of this distribution cannot depend on whether I decided to do it at the origin or I decided to do it far from the origin. So I will get the same PDF.
So
Okay.
Replace the spatial, this configuration averaging by spatial averaging.
By spatial averaging.
Because of the Gaussian nature of the field.
Yes and no.
It's
So
because of the ergodicity. Right?
it's because of the ergodicity. So even if it were not Gaussian, you would still be able to play this game.
Ergodicity come from that. Does that come from the Gaussian nature?
The ergodicity is coming from homogeneity and isotropy, from saying that I want to be able to take an average, and the average of the one-point PDF cannot depend on what position in space I decided to take it.
So if I have some model probability distribution apart from the Gaussian, and I still go with the assumption that there is homogeneity and isotropy, I can still do this
That's right.
placement of everything.
That's right.
So the main point is homogeneity and isotropy.
That's right. That's right. Yeah.
What you were saying, take nearby points and draw histogram within that, since they are correlated in spatial,
Ye-
it will not give a realization by realization average.
Okay. So let me try to say this little carefully. So there was the origin. So now I can take a position right next to the origin. Okay. So that's like saying P of x and y, or P of delta 1 and delta 2. Okay. So now I can do the same so I can do that in this realization, in this realization, in this realization, in this realization. And so now I will get a PDF that I would not draw like a Gaussian, but now it would be, the value at 1, delta at 1, delta at 2, or x and y. And I would get some shape, for how likely it was that they both had the same value, how, I would get some distribution that was a 2D distribution. Yeah. And this 2D distribution, I can now instead take one realization, and I can take the delta 1 and delta 2 that are separated by some distance r. And now I can go somewhere else in the realization, delta 1 and delta 2 separated by some distance r. It's always that same distance. I can make that histogram in this one realization. Yeah? And so the statement, the ergodicity statement, is that distribution has the same shape as the one where I always took the origin and r, but 1,000 different realizations. Okay? But now, you have to just be a little careful, right? That if I was taking this pair here, okay, and so it's true that I can take this pair here, or here, or here, or here, or here, and if I take that average, I will get a 2D distribution, and it will have the shape that we calculate for the ensemble statistics. So that's fine. Okay. The only thing to be a little careful about is in the ensemble statistics, this box is independent of this box. Okay? And so this pair was completely independent of this pair, was completely independent of that pair. Okay? So when I took 1,000 realizations, there were 1,000 different realizations, different pairs to make my histogram. Okay? In my single realization, this pair may actually not be independent of that pair. So when I took 1,000 realizations in this box, I have to be a little careful.
And that's where the requirement of homogeneity comes in.
And that's where the requirement of homogeneity is coming in. And so one way to say this is, so long as this box is infinitely big, Then there is huge volume where the stuff is not correlated with these guys. And so although it's true that there will be some that are correlated, I will have a big enough volume, I don't have to care about this difference. Yeah? But if I had very long-range correlations, which means essentially not homogeneous, then I couldn't do this. Yeah? And so if you want, that's the reason why it doesn't matter what the PDF is. It's not important that it's Gaussian or that it's multivariate Gaussian. What was important is that it was homogeneous. Yeah.
Because ergodicity in stat map has some different.
Yeah, yeah. That's right. So here, this is the spatial algorithm. Yeah, it's just space, that's all. Yeah. Okay, so this discussion is actually good because we'll be playing a lot of this game of doing averages over realizations in the next couple of days, okay? Yeah.
So when they try to say scale of homogeneity using
Yes.
correlation function,
Yes.
it's a kind of a catch-22 situation.
That's right, because there's, in the sense that people have made people have in the back of their head that it is homogeneous when they made the measurement. Now, there are ways to make measurements that are less susceptible to inhomogeneity, okay? And there's quite a long discussion in the literature about whether it really is homogeneous by making measurements of the clustering of galaxies, okay? And there are a few things that come with the clustering of galaxies that are how should I say it? There was an argument that you could not define homogeneity in the galaxy distribution, and so maybe the universe is a fractal, things like this, yeah? And there are things that happen in the clustering of galaxies that are inconsistent with this fractal expectation. And so let me set up a little bit what the correlation functions are. And then when we do the clustering of galaxies, just remind me to address this again. Yeah? Okay. Okay. So a Gaussian field is a sum of independent k-modes. Okay? I actually had this in a slightly different order. Let me flip through to show you these adding of k-modes, and then we'll come back. Okay. So the Gaussian field was this adding of independent k-modes, and so this is just writing out more carefully the adding, right? So this is that everything is just pairwise, that if I had more than pairs, then those expectation values are 0, okay? And then generating a Gaussian field, you have to draw the random numbers per k-mode, okay? It says 2 random numbers per k-mode. When I was saying it in words, then I was saying amplitude and phase. But phase means EIK phi, or EI phi, right? But EI phi means I can really think of a cos plus I sine. And so the amplitude of the cos and the amplitude of the I sine, those are the 2 random numbers that are here. Yeah? Because those are the 2 guys that would each be Gaussian. If I was thinking of it as a length and a phase, then it would be so the distribution of the 2 Gaussians is called a Rayleigh distribution, and the phi would be uniform on 0 to 2 pi. Okay? But that's a technical thing. The important thing is you have to draw just 2 random numbers, okay, per mode. And so I said, so we have to think, what is the power spectrum, meaning is the random number that I have to draw for a long wavelength the similar similar value to the thing I have to draw for a short wavelength, okay? And so let's look at this. So this one is for if the power spectrum as a function of k, which means p of k is proportional to k raised to n. And we put n equals 0, which means it's the same for all values of k. So it was the example I said in words, okay? Then we can imagine, right, that we draw the amplitude for the first one. That's the long one. And so if it fits in this box, then it was a wave that looked a bit like this, something like that, okay? Then we draw the amplitude, a wave which has half that wavelength and quarter that wavelength and so on. And so we add 25 of those together. The result of adding 25 is something that looks like this. This is spatial position. And the value is fluctuating because the amplitudes of the k modes, when you add them up, they give you this kind of complicated thing. Yeah? So it's just usual Fourier kind of thing. Okay. Now, importantly to do this, what did we do? Each k mode, we pulled a different random number, right, to generate it. So they were independent of the previous ones. So now we can continue this process, and we can add the next 25 modes. So we pull the 2 per mode, generate them, and the result of doing that is this. You can see that there are more here than here because there's much finer scale structure here. Okay, it's much more jagged. Okay, so this is when the power spectrum is independent of k. Now let's ask what happens when the power spectrum depends on k. So just to be simple, we'll keep it a power law, and I'll put n negative. Okay, so this is the result. Okay, so you can see two things, I think, right? So the first thing is that here you can see kind of big structure, whereas here it was kind of not there. Okay. And the second thing you can see is that when you went from 25 to 50 modes, not much changed. Whereas here you could clearly see that you went to smaller scale structures. Okay? Why is that? The power spectrum is k to the minus n. As you start adding smaller, so big K means smaller wavelength. As you start adding the smaller wavelength modes, their amplitude, you're drawing Gaussian number with this as the variance. This thing is becoming smaller and smaller. And so that means you're adding short wavelength waves, but they have zero amplitude. And so you're not changing what you saw on large scales. The large scale modes defined everything. Yeah? And so a power spectrum that has k, is declining with k, that's like, if you think of this as a sea, it's a calm sea. There are big waves, but no small crests on the waves. Whereas n equals 0, the white noise, that's a choppy sea, and that's this. Okay? And so the power spectrum, one way really to think of it is how much small scale choppiness is there in the density field. Remember the shape of the CDM power spectrum. K to the minus 3 at big K. Okay? So it's not very choppy at all. The large scale modes matter. But the CDM power spectrum is strange, right? It's a shape like this. So it's not very choppy on small scales. But on large scales, it's not like the k to the minus 2 or k to the minus 3, because it's also dropping down, because it's k to the 1 at very large scales. Okay? So there's a preferred range of waves that are determining everything. Okay. Okay. So this was jumping a little ahead to what the field looks like. Okay. Let's go back now to how we make measurements. So, okay. One other math trick. Yeah, the math trick is, we were talking about convolutions, right? So the convolutions in real space, the convolutions are a painful thing, right? A convolution would be P, I guess I can keep using this notation. P of S was the D of X, P of X, P of S minus X, right? So you have this kind of convolution. And so now I can think of the convolution. This was like a delta at X. This one is the delta smoothed with some window of some scale r. Okay? And so we're doing a convolution. Okay? And so that means we know from Fourier space that if I take the Fourier transform of this, then I will get the product of the Fourier transforms. And so, so the product of the Fourier transforms is delta k is the Fourier transform of this, and the wk is the Fourier transform of the smoothing window. If the smoothing window was 0, 1, that's the one we usually think of as physical, no? As we say, oh, everything inside 50 megaparsecs. I count that, everything outside I put to 0. Okay? This one is writing it more generally because there's no particular reason why I can't do the guy in the center, I give a weight 1. The guy further out, I give weight half. The guy further out, I give weight 0. So I decline smoothly rather than as a top hat. Okay? Or there's no reason that the smoothing be with a finite window. I could have a Gaussian that drops as a function of distance, e minus x squared. Okay? E minus x squared is a nice one to think about. Okay? So if I'm convolving with a Gaussian window, the Fourier transform of the Gaussian is a Gaussian. And so that means that this guy is an e minus k squared r squared over 2, if you're smoothing with a Gaussian. Okay? Yeah?
Here, you are averaging over all the points of within a scale of radius r.
Yes.
So the convolution must be whatever points which lie within that many number, according to what you said earlier.
Yeah.
The convolution of several variables within r. But here it seems like this convolution of just 2.
Very good. You're stating exactly the reason why Fourier space is so nice. Okay? So let's make this a little bit more explicit. Okay? So let's imagine that I have the values at many different points in space. When we think in real space, you're right. Okay? So let's take the origin. And around the origin, we want everything inside 50 megaparsecs. So I have to add up all these numbers. Okay? So if that's the value I want, then I come to this formula. Okay? And I say, if I want this at the origin, then this at the origin, I put x equals 0. If I put x equals 0, then I eikx is this guy is just 1. So then I will have delta k wkr. This is the Fourier transform of the guy I want. Okay? The k modes are the things that I already made my field. So I know my set of k modes. Okay? So I just take the same k modes. I don't have to do anything. I just give them different weights. Yeah? If the smoothing in real space was a Gaussian, the weights are e minus k squared r squared. Meaning k equals 0, I give weight 1. And when k is big compared to the r, I'm giving 0 weight. Okay? And so this will be the Fourier transform of this guy. So I have to inverse Fourier transform this, and I will get the one I want, the smoothed value. Okay? But the important thing about doing this was that it's like you do the sum, not of the different positions in space, but of the k modes with the correct weights. Yeah? Because you're still doing a sum over many k modes. You're just giving them lots of weights. Rather than giving all the positions in space equal weight, you're now giving the k modes the right set of weights. If I want to know the smoothed value at this position in space, then this term stays, because now I'm not at the origin. Yeah? But that's all. And then I do the inverse Fourier transform to get this at x. So the important point is that the smoothing operation is just giving the k modes different weights. That's all. But there's a good piece of intuition that comes from this. And I sort of said it in words. I said that when k equals 0, then e minus k squared r squared, that guy is 1. But as I go to big K, this guy drops. So the operation of smoothing is one that is throwing away the big K modes. Yeah? And that is what we think, no? The big K modes are the short wavelengths, and you're averaging out the short wavelengths, so they don't matter. So when we were doing this discussion of what is the scale of homogeneity, then you say, oh, you know, how big should R be so that my answer is, there's not big variation in the deltas. We'll come to this soon, yeah? But you can start seeing that to address the question of homogeneity, you're really asking, how big do I have to make this scale before things become simple? Okay. Okay. So we're going to use this quite a lot. Yeah.
So here the smoothing over a scale in a linear space doesn't mean that we are not restricted to one region. We are restricted to, like, we can go full space.
So let's do, supposing I was doing, let's do the one which is just a finite sphere in real space, and then we'll do like a Gaussian, okay? If it's a finite sphere in real space, then, so that means we're doing something like this, and this guy is a theta, which is cutting to 0 when this is bigger than R, yeah? So that means that I can do just this, yeah? That's the way we would think of the smoothing. We added up everything inside R, yeah? But so it's really some function like this. If I now do the Fourier transform of this, really I should do from minus to plus infinity over all space. And then I do the Fourier transform, you know, EIKX of this. Then I will come in here, I will do the Fourier transform of this to get my delta k, and I will do the Fourier transform of this function. The Fourier transform of this function is EIKX and EIKS, right? Then I will have the theta of S minus X ds, dx. If you do this one, then, so this was a 0 or a 1. Inside here, so these are all really vectors because it's 3D, yeah? So there's some angle between k and s. So there's an angular integral to be done. And the thing that remains is a Bessel function, because this is one way of defining Bessel functions. This is like a J1 Bessel function. Okay, so this one, the value of this integral is 3 J1 KR over KR. Okay, so this is just some trigonometry, sine KR minus KR. This, yeah, it's that kind of thing. Okay, so you can write it in terms of trig. Okay, but so this guy is something that oscillates, and so if you have something with a sharp edge in real space, 0, 1, or 1, 0, yeah, the sharp edge in real space, that will have oscillations in K space that will extend over all R, or over all K. Okay, so it won't be finite. Whereas if we had instead said, I want to calculate suppose I was instead smoothing with a Gaussian. That Gaussian extends over all space, it's a smooth function, and so the Fourier transform of it is also a smooth thing that extends over all K. Yeah? And so you can choose whichever smoothing filter you want to use, and you just always do this procedure. Yeah? It's a useful one in the context of Gaussian fields is if you say, what if my smoothing filter was 1 and 0 in K space? No? So I add my individual K modes and not the higher K modes. right? In that case, you can say, what does that correspond to in real space? And in real space, it will correspond to something that oscillates over all R. So that will be like smoothing, where you take, in this position, if I want to know the density here, smooth with a filter that is sharp in the K space, then I should take all the values here times 1, times half, times 0, times negative half, times 0, right? And so I will smooth them with a filter that is like this, sometimes negative, sometimes positive. And that will just be what the value is at this position, and then I can do it at any different position. Okay? But you can see that this operation of making doing the sum, if I was thinking in real space, each place I have to do a different sum. Okay? Whereas in K space, what do? So you start with my field, Fourier transform. So now I have all the K modes. I multiply all the K modes by the smoothing filter once, and I transform back. And the thing that is back, every single point in space has the correct smoothing. Yeah, so it's much more efficient. And then, in addition to this, there are fast algorithms for doing Fourier transforms, FFT. So this becomes an n log n rather than some n squared procedure. And so for big things, it's very fast. So there's a technical reason and a conceptual reason for doing it like this. Yeah. I'm running a little bit late. Let me just do one thing in real space, and then we'll stop. Okay. So we've talked about the power spectrum. And the power spectrum is something about 2 K modes. And so in real space, what is the corresponding thing? So what is the Fourier transform of the power spectrum? And so the Fourier transform of the power spectrum is something to do with the density at 2 different positions. Okay? And so I will write out the formula for that after the break. But I want to show you what it means to measure this thing, and then we can do the math. Okay. So a field like this is clustered. If we took if we made many small squares and we asked what is the density in each grid point, and we made a histogram, that histogram would not look Gaussian. So it's not a Gaussian field. This is the result of an n-body simulation. It's nonlinear. It is not Gaussian anymore. Okay? But we would like to make some estimate of how clustered the particles in it are. Okay? And so what can we do? Well, there are many different things we could do. There are 2 things that are commonly done. So here's one of them. This one is you sit on a randomly chosen point, and you say, I want to know how many points are some distance from it. Okay, some distance r. And so that's what this line here is drawing. Okay, and then so you keep this line the same length, and now you take this line to all other points. Okay, and so you want to know how many points had another point a distance r from them. Okay, and you just sum over all the points in the field. Okay. So why do you do that? Well, you'll get some number. So how do you interpret this number? So this number, what you really care about is how different are the number of neighbors, this separation. How different is this number from what you expect if they were not clustered? If they were not clustered, what do you expect? 4 pi r squared dr, number density of points. And so you do this count. You divide by the 4 pi r squared dr, number density of points, and subtract 1. Okay? And that thing is the correlation function. Okay? And so
That will be the integral of the correlation function.
only at r. Yeah, only at the r. Only at the r. Otherwise, it would be an integral. Yeah. And so there's the number inside the volume element V1, volume element V2. And so the idea is that you can write the joint distribution of having a particle in volume V1, a particle in volume V2. The joint distribution, I can always factor it as the probability in V1, the probability in V2 given V1, and V2 given V1 I can write as in V2 times a correction because of the V1. Okay? That correction we call the correlation function. Okay? This correction, we can now start applying what we think should be true of cosmological fields, which says, in principle it depends on the positions R1 and R2, but we think that the universe should be homogeneous, so it cannot matter whether the pairs I measured were here or were here. And so all that matters is the difference between them. And now it cannot matter if the pairs are like this or the pairs are like this. And so that's isotropy. And so the magnitude matters and not their direction. Okay, so that's the homogeneity and isotropy that enters here. And so, we will try to measure this in data, and I've kind of described how to do it, right? The density field, we could have said, is what is the number inside some little volume R. There's an average. We can do this, right? We can subtract the average. That's a delta. Okay? And so the correlation function is trying to estimate this thing. Delta at one position, delta at position R away, where R is this R1 minus R2. Okay? And so there are two common ways of estimating this thing. Okay? And let me see if I have it here. Maybe I have it written on the bottom. Right? So the thing I described in words was, I sat on each data point and I asked how many others were distance R from it. So that means I sat on data and I counted number of data points R away. So we'll call that DD. The RR is you choose a random position and you count the number of points that are distance R away from it in the random distribution. That's the 4 pi R squared dr. Yeah? That one we call RR, for counts in a random distribution, random around random. Okay? And so if we take the ratio of the two, then we'll get 1 if there's no clustering, and the correction to 1 is what we call the correlation. Okay? So that's a practical way of measuring this. Yeah? That's the algorithm you'd feed to a computer. And then you can do a little bit better than that. You can say, well, now I do some estimate of what's a way to make the measurement with the smallest possible error bar, so the minimum variance way of estimating this statistic. Right? And so I won't go into that, but if you're interested, ask me in the discussion section. The better way to do that is this combination. You do the data counts, you do counts between the data and the random distribution, and you do the random counts. And it's this combination that is the best way to make this measurement. Okay. All right. Now, the final connection is to take the Fourier transform of this guy. So we had got to the correlation function is pairs separated by R. Yeah? And then this is just going through the detailed algebra to show you how you're going to get a power spectrum from that they're power spectrum pairs. I'm running late. You're going to get the slides. So you have the algebra. Okay? So this is showing you, the angular integral and stuff like that. That's going to give you the Bessel function. And I will almost always, when I'm writing things, not write things this way in the next few days, but explicitly write it as the Bessel function. Okay? Just because sometimes people don't like seeing complex numbers, right? And so, okay. So that means that the Fourier transform looks like this. Okay? So this is the P of k is the psi of r with a J0 Bessel function, r squared dr. Okay? And so they're this Fourier transform pair. Okay? And then we had talked about the BAO yesterday, right, with the wiggles. And so showing you they're really true Fourier transform pairs. Okay. So that was one statistic, right? Number of pairs separated by R. But now we could do another thing. We could say, let me throw down some cell. We'll take a spherical cell. It could be any shape, but we'll do a sphere. Okay. We throw the sphere at random. And each time you ask what's the matter in the sphere, and then you could make the histogram. That was the thing that was Gaussian, now is not Gaussian. And because it's not Gaussian, we don't know what shape it is. By the end of this week, we will have made an estimate of the shape. But the zeroth order thing we'll ask is, what is the mean? Well, the mean should not evolve. It should be the background density. So the mean is the mean. But the variance can change. So the variance is the width of this PDF, the width of this distribution. And so we can ask, what is that quantity? Okay? And so we just throw these cells at random. And then we make the histogram, and we ask, what is the width of that histogram? Now, the width will depend on whether we threw big cells or small cells. Universe is homogeneous, we think. So that means on large scales, the variance should be smaller, because all the cells should be similar if the cells are very big. Okay? And so we want to know what is the relationship between the variance and the correlation function, or what's the relation between this statistic and the other one? Okay, both have to do well. So now it's not. Is it obvious that it's something to do with pairs? Yeah, it's obvious in the sense that it's what are we really doing? We're counting the number of particles in a cell. Then variance means we are squaring. And so if I imagine that I had delta 1, 2, 3, 4, 5, 6, and now I add them all up and I square, I'll get the delta 1 squared, delta 2 squared, but I'll also get the delta 1, delta 2, 3, 4, or 1, 2, 1, 3, 1, 4, 1, 5, right? And 1, 2, 1, 3, 1, 4, 1, 5, that's like the correlation function of separation this one, separation this one, separation this one, up to separation the size of the sphere. Yeah? And so that means that this is like some average of all the pairs between zero separation and the separation that is the diameter of the sphere. Okay? So it is really just some repackaging of the information of the pairwise, because the only thing I did was square. If I had done cube, then there would be something with triples. Then it would be more complicated. But I'm just doing square. And so the hope is that if the correlation function is something to do with power spectrum, Fourier transform, what is this thing in terms of the power spectrum? What is the variance? Okay? And so one way to think of this is to say, well, supposing what I had done was I had sat on each particle, counted. Okay, so I've done a convolution. And if I've done a convolution, then what I should do is I should do the convolution in Fourier space. And that means delta k has now become delta k times w of the smoothing window. And now I'm doing that squared. Right? Because I'm squaring the density at each point. Squaring the smoothed density at each point. And so that means that now what I'm doing is delta k now has a smoothing window. And now I'm doing the power spectrum, means I did this guy squared. So I'm doing something like this guy squared. And now I have to be careful because it's complex numbers. So I would do the delta k was defined with the delta function k1 plus k2 is k, that kind of thing. But basically this one is going to be the delta k, because this is the thing that fluctuates. My window is always the same smoothing window. And so I just get 2 powers of the smoothing window, which means this is the power spectrum with 2 powers of the smoothing window. Yeah? And then I have to Fourier transform that back. And so the relation between the variance is the power spectrum with the smoothing window, and that's it. You're just summing it up. Okay? Yeah.
See, when you said in the previous slide that you randomly throw these circles, will it matter whether the centers of the circles fall anywhere in space or on a galaxy?
Yes. Okay. The question makes sense? No? So it's whether they are randomly placed cells or they are centered on particles of the distribution.
Then there's a bias, that it is from a galaxy, how far is it?
If you take the spheres to be sufficiently big, it should not matter.
Okay, so we can quantify this. Okay? So in the thing that I drew that was randomly placed, what was happening was so all the deltas are smoothed. Okay, so it's really as I did here. We are doing delta, smoothed. Okay? If you're sitting on a particular particle of the distribution, then that's a particular place that you're averaging on. So that one, it's like it comes without its smoothing window. And then you smooth around it only. So you get this with one smoothing window, not two. Okay? That ends up being this thing. So another way of saying it is, in the correlation function, and maybe it's easier to see in the correlation function picture. In the correlation function picture, we were doing, one possibility is dx, dy, delta x, delta y, delta Dirac of x and y. And now we have to do the convolution to do the smoothing for each of these guys. Okay? So I could have done the convolution and tried to simplify this. That convolution will have brought the windows with each of these guys. Okay? The other is I could have done, so that's the thing that we're calling sigma squared. Okay? And there's some convolution window. There are two convolution windows sitting here. Okay. Now, in this one, I could have simply taken, I sat on a galaxy, and I asked how many other galaxies are inside R. So that's just the volume integral over that correlation function. Yeah, so that was like 1 plus the correlation function. I did the integral of this from R squared dr from 0 to R, right? And so there will have been, some 4 pi, this kind of thing. Usually the 1 we know it's going to give us the volume, so we don't write that guy, right? So we're interested really in this average, okay? And we know we're going to get this thing. So normally we would divide by the 4 pi r cubed over 3. That would be the normal thing, right? So if we divide this by 4 pi r cubed over 3, then this thing is called the volume average of the correlation function. Okay? And this one, this integral from 0 to r, I can write as an integral from 0 to infinity times a theta function, that r is less than r, and then it's a step function. And now if I take the Fourier transform of this guy, there was one theta function, so I'm going to get one window. Okay? Whereas this one, there were the two windows. So when we're doing things on very large scales, all the windows are basically 1 or they're dropping. And so that means that the 1 times 1 is 1. And so the difference between one window and two doesn't matter. But if I'm going to smaller scales and the windows are dropping more gradually, then this difference matters, and there's a small difference between these two things. Yeah? Most of the time, people work with this guy, but there are good reasons to work with this guy. Yeah? When we do, if we were doing more careful perturbation theory tomorrow, then this guy plays a key role, because if I'm thinking about, if I have two particles and they're correlated from the initial conditions, but after that, gravity is going to make them move. So they're going to move towards each other because of gravity, but what actually is moving them together? So what's actually moving them together is the total mass in the sphere between them. Yeah? And so that's a little bit like you have to think about what is the mass centered on a particle, or the mass centered on a particle, and that mass is what is having to move. And so for those kinds of calculations, this is the useful way to think. Okay. We might have time to come back to this, but that's the distinction. But this thing is easy to see in Fourier space, 1 window, 2 windows, and is not so easy in real space, yeah, because it's tough to see the effect of 1 versus 2 convolutions like that. So that's one of the virtues, again, of you do the analysis in Fourier and then you come back to real. Yeah? So that's the expression for the variance. And when the smoothing window is very big, then that means this is cutting very quickly. Always think of this as a Gaussian, E minus k squared R squared. Right? And so when R is 100 megaparsecs, then for k of 0.01, it's already cutting. And so this thing is a function of R where it has very small values when R is big, and it can have big values when R is small. And so this is describing the homogeneity. You know, if this number is small, universe is homogeneous. It means the spheres are all very like one another. And if this number is big, it means the spheres are very different from one another. Okay? So this is a very useful thing. We'll use it a lot in the next few days. Okay? The other nice thing about the Fourier space is now I can ask what happens if I counted, if I took counts in here, I took a smoothing of 5 megaparsecs, and there I took a 10 megaparsecs, and they are separated by 30 megaparsecs. Okay, so all of that we can describe quite easily with the Fourier space. Because with the Fourier space, you just say, okay, now the 2 positions in space, I give them 2 different smoothing windows. And so I take the power spectrum with the 2 different smoothing windows. What always enters is, I should have put this earlier. Sorry, I ended up putting it here. This delta k is a k cubed p of k. Okay, so this is, I just define as k cubed p of k. Now I have 2 different smoothing windows, and if those 2 different smoothing windows are separated by some distance, little r, then you put a J0.
What is the motivation for having 2 different smoothing scales in 2 different regions?
When I start doing bias tracers, then we think of them as being assembling their mass from different regions. So a massive object pulled its mass from a big region in space and a low mass from a small region in space. If I want to know if the big guy is correlated with the small guy, then I want something like this.
We both consider them as Gaussian. Both of them.
Yes, so the models that I'll set up tomorrow, we will do the discussion in the initial conditions, and then the next step will be how they evolve from the Gaussian field to the non-Gaussian late time. So it's a 2-step thing. Yeah? But so that means that, that we're all the time talking about smoothing, and often talking about smoothing with different scales at different positions. But in terms of the formalism, it's fairly straightforward because you just put smoothing windows and you put a J0 if they're not in the same position. Sine x over x is equal to 1 if they're in the same, if r equals 0, right? So if they're in the same position, this guy is just 1. And so that was this guy. The J0 is equal to 1 when the separation is 0, and that was just squaring the value, right? But if they're at 2 different positions, then you just put a J0. And so the correlation function that we had done before, that was one where there was no smoothing window, so you only had the J0. Yeah? So it's very straightforward with the Fourier space expressions to describe these fairly complicated things. In real space, these would be a nightmare. Yeah? Okay. Just to get some feel, right? So we already described a power spectrum that is a power law. And so let's let's calculate what is the correlation function if the power spectrum is a power law. And so we have to do dk over k, the k cubed, the p of k was a power law with some amplitude. And then you have to just do the J0. And so this is just some algebra you can do, and if this is a power law of slope n, this will be a power law of slope 3 plus n. Okay. Then we can calculate the variance. Okay. And if we calculate the variance, and we decide we want to calculate the variance where we smooth with Gaussian windows rather than top hat windows, then I have E minus k squared r squared over 2 for each window. So for 2 windows, the divide by 2 is gone. So now we can calculate this guy, and again, it will have the same slope, just a different amplitude from the smoothing. Okay. And the final thing is, so we've done it for the variance, and this one is, if I was taking the correlation function and smoothing it, so I was smoothing the field, I was smoothing the field and then measuring the correlation function of the smoothed field. Yeah. Then what do I get? So you get some other expression. Okay. So I'm just evaluating the things before. For n equals minus 2, you get some expression. Okay. So it's some analytic thing, and the reason I'm putting it here is that this thing looks like, if I go to large scales, then the error function of some big number, this guy is becoming like 1. And if this guy is becoming like 1, then this is becoming like the 1 over r. And the 1 over r is the slope of the correlation function if n equals minus 2. So it makes it look like the correlation function of the smoothed field is not very different from the correlation function of the unsmoothed field, so long as you are on separations that are large compared to the smoothing. So let me try to give a little more physical feel for this, right? So suppose that I had a choppy sea, and I measure the correlation function of the choppy sea. Then I will get a big amplitude on small scales because it was quite choppy. Okay? But if I smooth the field, I've removed the small scale choppiness. So when I measure the correlations, then I should get no extra additional contribution from small scale pairs because it's all smooth on small scale. So I will get a correlation function that, if my correlation function was a power law, now the power law will level off because the small scale choppiness is not there anymore. Okay? What has happened is that these pairs, the smoothing has, I can think of it as, scattering them. And so it has scattered the pairs out towards here. So there's a little excess pairs here. But there's much more volume here than here. And so I get for taking a lot of the small pairs and putting them at large separations, I make a small enhancement to the extra pairs on large scales. Okay? And so you don't notice it here. And so people's naive expectation was, the smooth field is irrelevant if I'm interested on large scales. I don't have to care. So I can smooth, which means that I can make, in data, when I make measurements in a galaxy survey, I don't need to measure galaxies every 1 megaparsec if I'm interested on the BAO scale, 100 megaparsecs. Doesn't matter, right? Because it's the smoothing, the fact that I have few tracers is not going to matter. And that intuition is not quite right? Because the BAO scale that is 100 megaparsecs, it's true. But the feature is like a delta function. Imagine now if I had this correlation function plus a delta function, and I now smooth this with a Gaussian. So the smoothing of this will reduce this power law in the middle, will keep this not too much, but the delta function will be hugely affected. And so it will look like this. No? And so people had thought, oh, I don't have to care about smoothing if I'm doing BAO physics, whereas it matters. Okay? If you're smoothing your field and then measuring the clustering, it's not the same as the original signal for the BAO. So be careful of that if you end up doing this kind of data analysis. And we're going to come back to the smoothing of the BAO soon. Okay, we already looked at these slides. And the final thing I wanted to show you before we start going back to physics, okay, is so we looked at the lots of small scale choppiness, small scale power for a power spectrum that is not flat, that is flat. Whereas if you have lots of small k, large scale power, but no small scale power, then you get a different looking field. Let me come back to this. So if you run simulations, where for the initial conditions you put Gaussian fluctuation field, so you drew the K modes from the way we described earlier from a power spectrum with no power, with same power at all K, or with n equals -2, you can see that the structures that form are different. You can see by eye, right? And so you can see by eye that this is a smoother C than this. This is lots of tight knots, okay? So tight that they look like little dots, but they're really all the mass, like this stuff, all collapsed to make little blobs here, okay? So you can see the spatial distribution by eye is different, okay? And so that's one idea behind large-scale surveys now, right? That we can just measure the clustering and tell something about the shape of the power spectrum from that. We can measure, the more precisely we can measure it, the more the clustering in the data, the more small details in the shape of the power spectrum we can tell, okay? And so the current interest is in whether neutrinos matter for cosmology. And the feeling is that the neutrinos, they move much more than the cold dark matter. So they will smear out structure more than the cold dark matter. So if I had this with neutrinos, it will end up looking more like this, because you will smear out some of the small scale structures. Yeah? They will not have been able to form. Okay? And so the idea is that there should be some imprint in the correlation function of the power spectrum of the neutrinos. And so people are looking for this. Right? Okay. Now, we can look for stuff in the shape of the correlation function of the power spectrum. And that's, yeah.
So when you look at this, so these simulations are at the same Z value?
Yes, they've been set to have the same power today. Yeah.
Because otherwise, things could change because of the nonlinearity.
That's right, yeah. So they've tried to set this up so that is matched. Yeah. One thing that happens with the scale-free simulations is that there's a sense in which you can normalize them so that you really can get the same fluctuation power. Yeah, so it's done fine. Sorry, there was a, yeah.
When you said smoothing of the correlation function, smoothing is done in real space.
Yes.
So then, when you said the Bayesian acoustic oscillation, the delta function also gets smoothed. But smoothing is in real space, so how does the delta function get smoothed in Fourier space?
Oh, that is also in real space. So the delta function was in real space. Yeah, yeah. So it's also smoothed in real space. Yeah.
So to set the same variance at the current time, would you set the sigma in to be?
That's right. Yeah. So you have to set.
Sigma is computed at the current time.
That's right. Wait. So there are different conventions. But so for this, so remember, so the point he's making is, if I have a power law power spectrum, then the variance is a function of R, okay? And it's a different function of R depending on the slope of the power spectrum. And so when I say, oh, they've matched the simulations to have the same amount of structure, I can only match on one scale, no? Because this is two different functions of R. And so the convention is try to match on a scale that is of order 10 megaparsecs. The convention for historical reasons is 8. So we call sigma 8. And so that's the kind of thing that is done. Usually these are matched to have the same power in a sphere of what would be 8 megaparsecs.
Yeah, also in this 8 H inverse, is it to do with this nonlinearity sets in or something? How is it selected?
Yeah, so it was originally selected because it was thought to be big enough that nonlinearity doesn't matter. That was the motivation. That's right, yeah. And so then there's also some confusion in the literature because some authors, they define it to be sigma 8 at redshift 0, and others define it to be sigma 8 initially. Because at least if it's sigma 8 initially, we know what the power spectrum is that we're talking about. Whereas if it's some other time, then it means different things. So the people are gradually switching to everyone agreeing that sigma 8 means at the initial time, evolved according to linear theory to redshift 0. So the power spectrum that has the linear theory shape rather than the other one. No, I'll show a picture in the next set of slides and then ask me again. Yeah. Okay. So the final point to be made is that so far we only did 2-point statistics. And I mentioned in passing that we could have done triples and stuff like that, no? And there's useful information in doing triples and 4-point and stuff like that. So this is a picture that shows you two distributions that have the same power spectrum. Okay, so it doesn't end with the power spectrum. It's useful to measure the higher order stuff. Okay? So this is basically a Gaussian field with the power spectrum, and this is some non-Gaussian field with the same power spectrum. Okay? So there's definitely information in the higher order moments, and there's some discussion in the field about what's the right way to quantify this information. Yeah? And since we won't do too much of this in the rest of the course, let me take a couple of minutes to describe that. So one thing we already described, which was you make a histogram, and you ask how does it look like a Gaussian. And if it's, we've already made the point that if the distribution is non-Gaussian, then maybe when I make it on 100 megaparsec scales, this distribution will look kind of Gaussian. But as I go to smaller scales, it will not look like a Gaussian. And as I go to even smaller scales, it will look different again. No? So it will be some scale-dependent thing. It will be some complicated thing. Does it make sense that if I go to 100 megaparsec scale, some big scale, it should look pretty Gaussian? It should, because remember, nothing moves more than 10 megaparsecs. So if I'm looking at 100 megaparsecs, everything that was inside here is still here. I mean, a little thing went out of the edge, but almost everything is still there, so the density didn't change. So on large scales, it should still be Gaussian, but as you go to smaller scales, it won't. So one thing you can do is you can measure this shape. Okay? But now, with all things that you measure, you ask, how well can I measure what I want to measure? And so if I want to measure the shape, usually the peak is the thing I need the least amount of data to measure. And the tail means it was unlikely, so I needed more cells to be able to measure it. So I needed a bigger survey to measure the tails. So it cost more. Okay, so you can ask, maybe I don't care about the detailed shape. Maybe instead I want to just calculate the moments. The first moment, the second moment, the third moment. The first is always the average, but the variance, which we did, then I can do the delta cubed, and then delta to the 4, and so on. Yeah? So I can, instead of looking at the shape of the PDF, I can look for the moments of the PDF. So that is the way the field has gone, is to look for the moments of the PDF. And then you can ask, do I want to look for the moments of the PDF using the variance, the correlation function, or we do the power spectrum. So the 3-point function in Fourier space, which is called the bispectrum, the 4-point function in Fourier space called the trispectrum. So do I want to do that? Or like I do the variance, do I want to do some smoothed 3-point thing in Fourier space? Okay. And so the field has gone in the direction of doing 3-point function in Fourier space. Okay. But these other things are wide open as well. Okay. Okay. We were talking a little bit about the scale of delta sigma 8, why that was picked. And so here is one way in which that estimate is made. Okay. So the variance is some function of R, the smoothing scale. Okay. Now, this variance is a delta squared. This variance for a fixed smoothing scale will be a function of time, because in the initial condition, so if I fix 8 megaparsecs, then in the initial conditions, the universe was smooth. But as time goes on, the universe gets more clumpy, and so the fluctuations from one sphere to another, they start to increase. Anjan made a simple estimate of this. The delta initial grows by a growth factor. Yeah? In K space, you just multiply by the growth factor independent of K. And so that means the power spectrum has the same shape. You just change the amplitude by the growth factor. And so that means that this thing, if I put the power spectrum will basically be the initial power spectrum times the growth factor squared, because the power spectrum is 2 deltas, so there will be 2 growth factors. And otherwise, and then I will just do the integral. And so the growth factor comes out of the integral. Yeah? Because it doesn't depend on K. And if it does that, then this is just some number that depends on the smoothing scale times some function of time. Okay? And so that means that this thing, we already made some estimate, is r to the minus 3 plus n for a power law. And what's going to happen is that now this will grow with some growth factor. And so we can ask, when does the value of this integral, which is some number that is depending on r, at fixed r, when does this number equal 1? When it equals 1, it means that the fluctuations from one sphere to another are order unity. And so that's like this place is very different from this place.
I don't know if this is hidden in what you have said. This WKR, I mean, you're having the same window function for all times?
Yes, so in this one, yes. I'm just imagining, I take a 10 megaparsec sphere and I ask, if I did this, it looks Gaussian in the initial conditions, and at late times, what does it look like? Yeah. And where the crude statement is, well, on 10 megaparsecs, this power spectrum is still the linear theory times the initial shape. And so I do the integral once and for all, and then I just change it.
At what scale should I average or smooth to see homogeneity at different times?
This is not necessarily homogeneity. I'm just, something.
Some measure of that.
Yeah. So in this case, the measure of inhomogeneity, if you want, is that this variance equals 1. Measure of homogeneity is that this variance equals 0.01 or something. Yeah. So when is this order unity? And that will give you a scale. This will be a different scale at each time. And so that is an estimate of on what scale is nonlinear physics required that this analysis is breaking down.
At a particular epoch.
At a particular epoch. Yeah. So at early time, it will be a certain scale that has this that is nonlinear. It will be some very small scale. Gravity didn't have chance to do anything. This guy is a power law, remember? It's a steep power law like this. If I need the value to be 1 and the amplitude was small, I have to go to very small scales before it's high enough. And then at late times, it's higher, so I can go to a bigger scale before it's order unity. Yeah? And so this is the way of estimating the scale on which linear theory breaks, and we have to do something else. Okay? And so that's what we're going to estimate now, is what we should do if we want to go beyond linear theory. Okay? Because we see that this variance on scales of, so many of you will know sigma 8 is 0.8. So spheres of 8 megaparsecs are almost nonlinear. Yeah. So if I want to understand the universe on scales smaller than 8 megaparsecs, I have to do nonlinear. I have to go beyond linear theory. But if I want to do things on larger scales, linear theory is going to be pretty good. The problem is that nowadays, we want to do things even on larger scales. When we want to do things, we want 1% precision. And so for that, we really do need to go beyond linear theory, even on 10 megaparsec, even on 20 megaparsec, even on 30 megaparsec scale.
The price of greed.
That's right. Okay? So now we go back and we start doing a little bit of physics for going beyond linear theory.